Welcome to the UCI Steel Bridge Team 2026 video submission. In this video, we will break down the design of our bridge, explaining the process that led to our final product, and exploring how the problem statement and sustainability influenced our design decisions. Despite our continual progress since our inaugural season in 2017, our bridge has ultimately failed to withstand loading for the past 2 years. Coming into the 2026 season, we have one main goal: apply everything we learned from these setbacks and set a new standard for what UCI Steel Bridge Team can achieve. Our final product is a reflection of this collaboration and application of all the unique skills each team member brings to the table.
However, this season's work kicked off long before the challenge was even released. At the beginning of the year, we reached out to hundreds of sponsors asking if they'd be open to help support our team. This dedication eventually landed us several generous sponsors, and if it weren't for this crucial step, we would have none of the steel, bolts, or other materials we needed to make this vision a reality. So, how did we settle on the bridge you see today? We started the design process by determining the main constraints that would help define our bridge. Our bridge is a 1:10 scale of a real bridge that could be built over a section of the Rio Grande north of El Paso, Texas, along with providing structural support and stability for pedestrians and emergency vehicles. The bridge needs to have enough clearance to allow passage under the bridge.
We focus on minimizing environmental impact both by avoiding encroachment on the river's navigability and by not impeding on the riverbank. The bridge utilizes a segmented design so that it can be constructed without piers and then extended across the river using temporary barges. This reduces the risk of pollution and disturbance to the river. We ultimately settled on a pony truss style bridge with the required cantilever, which allowed us to reduce deflection and bending moments. This design decision was based on the given bridge envelope. By implementing a Virendale inspired truss for the lateral system, we improved stiffness and torsional restraint. We decided to continue with 4 separate footings and opted out of using the whole rectangular footing box. This was done primarily for sustainability reasons, as the reduced weight would lessen the intrusion to the riverbank. To begin construction, one team member will bring all the pieces and tools across the transportation zone while the remaining 3 act as barges. 3 barges then build the main stringer from west to east before constructing the upper truss and connecting the laterals. The last team member simultaneously constructs the cantilever after the transportation phase is over.
Design software such as AutoCAD, SAP 2000, and SOLIDWORKS have been invaluable for creating realistic models of our bridge as we continually evolve our design. AutoCAD is both the first and last of the digital software that we use. Our initial sketches are first recreated in AutoCAD by drafting each member, how they connect, and how the overall design of the bridge will look. By the end of the design process, we use finalized shop drawings to kick off the fabrication process. After creating our design in AutoCAD, we imported it into SAP 2000 so we can simulate loads and find the shear, moment, and deflection of the bridge. We also assign member sizes and materials to determine the optimal size to use. One of our major takeaways from our bridge's collapse last year was a renewed focus on the design of our connections. Using SOLIDWORKS, we simulate how the forces and moments will impact our connections and ensure they are designed to withstand the applied forces and resulting deformations.
It takes a village to design and build these bridges, and nothing exemplifies that more than our fabrication process. After receiving our shop drawings, Alessandro High School welding instructor Joshua O'Neill involves the students by allowing them to practice welding, cutting, and grinding on portions of our bridge.
Build team prep begins several weeks before fabrication starts. Through several rounds of tryouts, 4 build team members will be selected. Once fabrication is complete, they will have several weeks to master the construction of the bridge. The design team took into account the construction process by maximizing the dimension box to reduce the number of pieces and the amount of time it takes to construct the full bridge.
As a team, we recognize that sustainability is of utmost importance to the field of civil engineering. We strive to go beyond simply designing a bridge that has a low environmental impact on the proposed site by having our steel serve as a learning tool for students, as well as utilizing rigorous digital testing to avoid using excess steel for any last-minute changes to the design. And through metal donations by Tally Metal Supply, we reuse steel that would otherwise go through a resource-intensive recycling process.
This bridge represents the dedication and collaboration of the UCI Steel Bridge Team. By focusing on the site's constraints and the bridge's purpose, we made intentional design decisions that meet and even exceed the project's demands. Our design emphasizes sustainability and reliability while balancing aesthetics with minimal impact on the surrounding environment. The UCI Steel Bridge Team would like to extend a final thank you to our sponsors as well as the University of California, Irvine for their incredible support. Good luck to all the other teams, and one final thank you to AISC and ASCE for hosting this competition.